Right, so this is a presentation on engineering a machine learning pipeline for extracting automatically, obviously, metadata from the longitudinal survey questionnaires which are held within Closer Discovery. And I'm here on behalf of all the co-authors on the paper who are listed on this slide. So to give a brief outline of my presentation today, I'll start with some background. And I think people here are more experts on that, but just to give a context to the presentation. And then move on to the problem that we tried to tackle in this ESRC funded project. And before moving on to the approach that we adopted for this, which was engineering this machine learning pipeline for extracting the different parts of the questionnaires, which are held within Closer Discovery. And then I'll finish with some of the experiments and the results that we got. So these are more or less initial results that we have. We have moved on with those. We can talk a bit more about those as well. Okay, as I say, three main players to give a context here. Obviously, first and foremost, DDI lifecycle, which obviously has this rich metadata model for capturing the not only the content of questionnaires, social science or biomedical questionnaires, which we took into account for this work, but also capturing the flow of the questionnaire. So these are instructions to the interviewers, the questions themselves, different statements of the response domains, etc. We'll have a look at some examples later. And not only it captures the flow, but also it has the support for versioning and provenancing objects. So for example, by using this based on construct, which allows reusing questions in different studies, and also sort of comparing and analyzing studies as they have evolved, which is quite useful to have for longitudinal studies. Then we have the archives of the question banks, which have all these surveys, mostly in PDFs, stored in these archives. But what we are missing is most of these archives, the questionnaires, the questions and the response domains are not linked. So if we really want to start reusing questions, we need this rich sort of metadata around the questions. So for example, what were the possible response domains, to whom it was asked to, who asked the question, and so on. So all these measurements. Then the third most important player for our study, Closer Discovery, which houses these question banks for social science and biomedical domains longitudinal studies, which have been processed according to the DDI life cycle. And these are processed and marked up in XML. However, most of this was done manually or at least semi-manually over a number of years. So we have these marked up questionnaires in Closer Discovery, which allows us to search for questions and also possibly reuse them in new questionnaires while designing new questionnaires. So what is the problem there? So as we have seen, we have new questionnaires coming in. We have had quite a few related to COVID-19 already. So what this means as the volume of these questionnaires increases, and these have to be added to Closer Discovery. And if we want to really scale up to provide this high quality question banks, this is where doing this manually, throwing manpower at it becomes a bit burdensome. And then we start thinking of, are there any automated methods which are still efficient and robust enough to extract all of this metadata and data out of related to question items, we took question items as our starting point for this work to extract this automatically and populate these question banks. And so we started looking at machine learning methods, more specifically supervised methods, to see if we can automate this extraction of valid DDI items from the survey questionnaires. And we used as our jumping off point I'm trying to move the bar away, the marked up questionnaires which form part of closer discovery. So if we see this diagram on the right, that sort of explains what we tried to do. So we have the marked up questionnaires in closer discovery right at the top here. These are in XML, and we extracted these to form our training data, because what we do with supervised learning techniques is we train a model not by specifying in code. So we don't have any rule-based mechanism saying a question would look like this. A question would, for example, end with a question mark, or it will start with why, what, how. We let the model learn by itself by looking at a range of data. So we extracted this using the Closer Collectica REST API. And this formed our input data. So part of that was used for training our model. So that links to some percentage, and we'll come a bit later on the different percentage splits, form the training data set. And after model training, it formed the trained model, which is then stored and then ready to be tested with different questionnaires. So we started with the test data. We looked at certain PDFs, extracted that, which was just scraping that, just getting texts in different lines, and then try to see how well our trained model is able to distinguish the different item types of DDI lifecycle, how good it performs by extracting questions, conditions, instruction statements, so on. And then, okay, so it seems that we have got a candidate approach in mind. And this basically then boils down to text classification problem, and it's a multi-class problem. So we have different item types that we want to identify and classify from each other. So how the different machine learning pipelines work is we usually try with different sets and subsets of input data, and we also perform some feature engineering methods on this data. So what features of the data improve its performance, for instance, and what are the different parameters of a model. So for instance, if we have different layers of a machine learning model, we have different weights of how we connect the different layers together. And this is something which the model learns as it trains itself. And then we have obviously the resultant outputs. So we are trying to evaluate the model based on accuracy, based on precision, recall, and so on. So we have, as we start actually working with the machine learning pipeline, we see that this sort of blows up quite early on. We have all these different combinations that we want to keep track of. And the way sometimes we work is we have input data, we want to try with something else, we comment it out, and then uncomment the next line with the next combination. And if the software engineer is no longer around, we sort of start losing that knowledge. And we then thought, is there a better way of sort of capturing all this metadata with all these machine learning pipeline combinations that we have tried out? So we looked at this sort of second sub-problem as well of documenting this experiment metadata so that we have some comparative analysis of and provenance of the machine learning pipelines as well. Excuse me. Okay, we looked at two different technologies for this. First is the data version control, or DVC, to abstract all of these model parameters, which includes the input data, the parameters of the model itself, the different outputs from the different pipelines, and also attaching metadata automatically to each of these model experiment through the ProvLake open standard, which builds on the provenancing of objects, which is Provo, the W3C standard, and sort of modifies that for machine learning. Okay, so quick context to the different parts of the questionnaire. On the right here, we have question with some response options. So we have the question label, which is the A1 here, and the actual text of the question. Do you ever have a EDDI? And the response domain, in this case, we see it's sort of Likert scale. And we also see here that what we call it the code list. And what it does, it basically attaches different values to the different categories here. Another example here is, okay, I seem to be moving around things a lot, sorry. Give me a second. Is this second example where we have some statements before the actual question, and then we also have some conditions for this question. So if a certain response is selected, then there is some instruction to basically skip some questions. These are the different bits which we extracted from Closer Discovery to form our training data set. And this is the count of the different DDI items that we had in the entire data set. So this includes both the training and the test data set. So we had about 40,500 questions, some 3,000 instructions, 7,500 statements, and then different types of response domains that we captured to come up with the final 180,000 rows in the entire data set. Then we move on to the actual pipeline. So as I said, we have obviously all come across Git to version our code base. But in machine learning pipelines, we have to version not only the code base, but keep track of what input it was attached to, which was the best performing, and what were the resultant outputs for all the combinations of the experiments. And this is where DVC helps us because it can do not only data set versioning, but also experiment tracking. And how it does this, it versions the state of the input data as it evolves through the different experiments and associates that with git commit hash. So when we commit that code base, it calculates the MD5 hash. And it is then able to transfer via SSH this version data to some remote storage. For this, we use the UCL remote data storage facility. That's a petabyte scale storage facility for all experiments, which use the high computing cluster at UCL, which we use for our experiments. So we have remote SSH access, and this. So this is the this box on the right. So we used it to store not only the different data set versions, but also the trained models. So we have cleaned committed versions there. And this is the link between the local Git repository, which we check out, and we work with the trained model, the code, and the input data. And this is the remote GitHub repository where we are committing with each experiment. So just quickly, what DVC is allowing us to do, it is integrated with Git. And for each experiment, we can see it's an experiment will be hashed and stored. So we are not in each branch. So if we see this diagram here, might make this a bit clearer. So we have each branch for every model type. So for example, in this presentation, I'll walk through multinomial naive Bayes, which is probabilistic model. So it will basically calculate the probability of piece of text being question text rather than being an instruction or a statement or a response domain or a question name and so on. So that's how multinomial naive Bayes here works. And we see here that this branch is about multinomial naive Bayes. And what is, I'll just step through some of these important bits. So we have the data folder. Then we have the output directory where we have all the outputs for the different experiments, the source folder, and then we see something like the .dvc and also this dvc.yaml file. So what are those? So I'll explain this with this flow of how the pipeline works. So it starts with a DVC project and starts off with some steering code, which takes some input parameters from this YAML file, which we just saw in the previous slide. So what the YAML file has, it has the different configuration files of the source files, which need to be called in order. And it also has the input parameters, so which data to bring in. So the data is then picked up, it is cleaned. So for example, if there are any null values, those are removed from, those rows are removed and so on. And then it also creates this output directory. So the output directory will have for each of these experiments, one folder which says what were the, so here we have the evaluation metrics, what were the accuracy values, what were the precision, recall, F1 score, what was the ROC curve, which is output as an image file, and what was the confusion matrix. And then the steering code takes this clean data and the input parameters, and then calls the model specific code. So in this case, model is naive Bayes, and which is then initialized. And then if we have some features to generate, then it works with that data. So in our case, we generate for each word in our content. So for example, we had the content going in saying, how often do you have a headache? So it will take each word of that sentence and generate the vector. So it will generate the TF5DF vector, which basically gives the relative importance of each word in that sentence, and it will just generate index value for it.
5 minutes.
Then, sorry, how many?
5 minutes.
Okay, thank you. So then we train the model by running through the data set. And we also have in our YAML file some instructions on how we split the train versus the test. So we have 60% of the data we use for training it. 20% is to fine tune these parameters, and the last 20 is used as the test data. So we take this trained model, which has already been trained using the 60%, and then we pick up the test data, which was not used for model training, and then we run through the model evaluation, and what are all the values of these model metrics are then stored in the output directory, which is then pushed into the remote GitHub repository, and the train model is also pushed to the remote RDSS storage. Something else we do in addition for the model learning its own parameters, we also do hyperparameter tuning. So for instance, hyperparameters, we can think of how many runs should this model train itself for. So should it train itself for 10 steps? Should it do it for 50? And how we track it is we usually have a loss curve. So when the model runs, it is trying to minimize a loss function. So we see that if the loss curve goes exponentially, it's sort of decreasing. And at some point it reaches a minima, after which if we run it for more runs, it doesn't really make so much of a difference. So we also track those, and we use grid search, which is just a library in Python scikit-learn to run over, or rather loop over, all the hyperparameter combinations. So this is the result of logging all of that metadata regarding the experiments. We see here naive-Bayes model is our model name, and the inputs. So it will have values of the input data it starts with, where smoothing is the hyperparameter that we use, and it has all the values. So we see here there were a number of values here, 0.0012, starting with really small values. And then we have the associated output of this. We have the different evaluation metrics values, the FN score, the mean test accuracy, precision of recall. So I think what the important point is here, that we can sort of have this as model provenance. And we also, if we try to see what combinations worked best, if we are going back later point and saying, should we try something new? We also have something to help us in the recall, saying, we already tried these combinations, it didn't work so well. And the best performing is the code base, which was retained. So just to wrap up, we proposed here a supervised machine learning pipeline approach for automating the metadata extraction from the PDF questionnaires. And we also looked at the challenges of data and model version control in machine learning pipeline. We have some successes in generating in an automated manner, not only this metadata for the experiments to track the various combinations of input data, model features, hyperparameters, and the evaluation metrics values, but we also have successes in getting the different DDI lifecycle items out. And what the DDIL also allows that it has this provenance structure, and we have also the question text linked to the question URN, which we can also use for further analysis. That concludes my talk, and happy to take any questions.